Thank you for the opportunity. Also, thank you for inviting us a second time here. Looks like it did work out last time, so works out this time too. Those are 380 hearts if you want to take them out. I'm originally a musician, so if you give me a grand piano, you might have also joy. But I try to provide some value at the end of this day. And has been a very interesting task to listen to all the AI discussions today. And I thought, okay, should I have changed my presentation or modify it, because I'm talking about something old, confidential compute. In reality, the mathematics behind artificial intelligence is similar old. It's nothing new. Nowadays, we have enough compute power, we have enough storage, we have enough training data, we have enough throughput. All this is fine. So why to talk about confidential compute? If you run an AI agent, do you want to sit on the same computer as someone else with this agent? Most likely not. If you do your inference, do you want to do this on the same chip like someone else at the same time? Most likely, yes or not. It depends on your CPU or energy usage. So therefore, confidential compute comes a pretty important topic, especially with the actual situation that there are not enough chips on this world to feed our society's AI hunger or our AI appetite. I think that's the best word. So, and that does mean we need to address that. And while I have two economic slides here, I really try to make bridges between topics. So, and an attacker needs to win once. Okay? As a defender, we need to win all the time. I'm working for the office of the CISO of AWS, so I help to scale our CISO, Ms. Amy Herzog, into meetings like that, or internal and external stuff. We need to win the game or the battle of defending us and the internet every day. Which does mean the attacker knows when he has won. Maybe he drives away his Lamborghini because he's just sold all your data somewhere. We never know. For a CISO organization, you always have a situation where you need to prove that the investment into the organization is on the right spot. And with AI, the organization starts to consume energy in the AI models and starts to consume more tokens, and that also leads into that. But I want to go into something else. It's this one here. As soon as you share resources, you have a security challenge. It's also an old problem. If you share your space on a mainframe in the 70s, you need to do good scheduling. Nowadays, if we roll forward some 50 years, you will need to share your resources on the GPUs, potentially with someone else, because there are just not enough out there. And whenever you start sharing something, you need to take care of the security of the sharing. I typically also use the picture of houses. If you have a house and have several apartments in the house, having doors and locks is a good idea, right? You need to do some secure stuff. Otherwise, you don't feel well. You might not be in a problem. Yeah, I've heard, for example, in Canada, some people leave their door open because it's a more, let me say, peaceful environment, but I also know environments where you never would leave your door open. So it depends on what's around you. And if you do IT and if you send your token somewhere to be analyzed, you don't even know where this is. So we need to address that. And that does mean we need to address sharing compute resources. So, and it's all about that. It's about a chip. Who knows what's the supply chain of a chip? The supply chain of the chip is going back into sand, most likely from Florida. And it's basically going down into things like that. That's a wafer. And if we look onto production things, a wafer looks like that. That's a plate of monocrystalline silicon. Now, Mr. Dorn, what has that to do with share? I can tell you, if we would have enough of those, we would print enough chips that every one of you could do inference on his own super AI computer. Well, this is just sand. Okay, it's melted, it's super clean, it's carved into all those plates. That's a very intensive process just to get to this plate. Why don't we do that? Because the space on these plates is super expensive. A typical chip of your laptop might be the size of a fingernail on this chip, on this wafer, but the space on the wafer is limited. This is a limited resource on this globe. So that does mean we must share those chips. We just don't have enough of those. So, if we share those chips, we exactly come into the problem that we need to address that. The other limiting option here is labor. Not all of us do have the possibilities to roll out their inference supercomputer in the basement. There are not enough administrators to do that on the world. There are not enough engineers to build all those buildings, power plants, cooling systems. Again, we are sharing the chips and we are sharing the administrative resources. Otherwise, as of now, it wouldn't be possible. There might be a feedback loop in the future. The AI system might orchestrate itself, but then we are in a dystrophic possible future example, which you can read in books and movies. I don't want to look into this glass bulb. I want to state where we are today. Today, we need to realize that if you want to do this quick and fast, you need to have the resources. And most likely, you need to have the resources locally. Locally does mean not necessarily on this other side of the globe, maybe with a latency of some milliseconds. We are on a networking conference. You know all that. We get the questions, and I had the questions also last year. Well, where are your data centers? Who has access? But that's exactly the right questions. Who has access to the chips? Who has access to those things? Who is doing the labor, doing the work to keep this running? And how do we build security into those things? And that is starting again on the chip. We need to design the chips the way that we can share those resources. So, having said that, there are several technologies out there. Our friends from Intel and AMD will tell you, yeah, we have confidential computer requirements. Others will tell you we have this and that. Some people will tell you that they like RAM encryption, so memory encryption. They think it's protecting against sharing. But it's more important to keep all this together. It's very important to make sure the complete picture of sharing resources in the compute area is done right, so that you can do your inference, your compute, your AI, or your database query in a reliable and secure way. So, I don't see my preview, but we'll see. With AWS, I'm from AWS. I need to talk a little bit about our products. We took all those learnings about sharing and put several of those possibilities into our chips. That does also mean we have some very interesting strategies which are related to chips, which are related to AI, which are related to what you have heard today. Our first strategy, if a customer provides us with code to run, we will not place this customer on the same CPU at runtime with another customer. So we try to avoid sharing. We try to not put active code from customers together on the same core. This has economical impact. The most people, I'm doing cloud evangelizing now 12 and a little bit more years, think we are living from over-provisioning. We're living from taking 64 CPUs and selling them 128 times. That's exactly what we're not doing. If we have 64 CPUs, we map them to 64 customers, or less. In the agentic AI way, that's also very important. Where's your agent running? And with our product called Agent Core, we continue this strategy. Every customer agent is on its own CPU. It's on its own core. Depends on how you define CPU. We continue this strategy. We have done this with our compute infrastructure. We are doing this with our database infrastructure. You might think, well, what's database to do with code? Well, stored procedures are code, right? Stored procedures are executed on the CPU. So we are continuing that also in the AI area. We might not be able to do inference on your own cores, but we are. If you take the right option, yes, it's possible. But for agents, if you run something as an AI agent, we want your AI agent to be on its own infrastructure. Because we rather bite into the economical impact of not selling more than we bite into the risk with potential additional economical impacts of putting customers together. And I can tell you, for those who are longer here in the industry, this kept us out of a lot of stress. There's things like Spectre and Meltdown. If you have heard about that, if you're not, read it. It's a good story to read. With our strategy, it kept us out of that. So everything starts with security. We must put this in. So this is not only a marketing, we're great message. This is an built-in, must-have. I wouldn't even say function. It's a must-have capability. Because we provide shared computers. If we wouldn't provide this in a secure way, you wouldn't like it. And with cloud, so real cloud is paid on demand. It's not a, well, give me the money for the next 24 months cloud. Cloud is pay as you use it. Cloud is pay as you go. So if you don't like our agent core, you just can be out of that in the next minute. Not in the next day. Technically, you can just stop using us. So that puts us into the spot of us to be mandatory secure. Security is not an option. It's not a feature. It's nothing you buy additionally on top of the service. Security must be in there. So this is exactly why we put all this in. And in the compute area, it must be all there. And of course, you stack it. We could build layers. We could build slides with onion rings or slides like pyramids like that. But basically, if you run into a situation where you ask about, well, how do I do my agents? How do I start making my compute? How do I implement my model context protocol service? Ask all those questions. Well, not this. Ask all those questions. Address those layers. Dive deep here. And yes, there are solved problems out there. For example, sharing storage. Sharing storage is solved. Something which we know since a while. The ciphertext can't be seen. We map storage one-to-one. Encryption is a very important aspect of securing storage. Encryption helps with sharing storage, but that's not the silver bullet. The silver bullet is the one-on-one mapping between components and customers. And yes, there is sharing of network. Whenever you send something over the network, it creates risk. I think that's something which we all know already. I'm a child of the Cold War. I've been told, well, whatever leaves your building will be read by others, and yeah, that's what I'm working on. So, if you go with AWS, we are already in the area of post-quantum compute. Several of our systems are already on algorithms which address the post-quantum compute situation. For example, with S2N, the signal to noise, it's our implementation of TLS, or libcrypto, where we already have those algorithms implemented. So we're safe. But what's missing? And the missing aspect is something you can see here. Those are so-called DRAM chips. This is your memory. What's not really seen is on the lower end there is a CPU. And yes, you can move in, and that might be an overkill at the evening of such a conference. Well, that's an X-ray of a chip. You can see the core, this is where we don't mix, and then you can see the shared attention word, the shared cache. That's an old Pentium chip, by the way. So it's public knowledge, nothing from me. So if you encrypt something, the chip is calling the memory, and yes, that's solved. Talking to main memory is solved with encryption. Talking to these things, those are host bus adapters, connection to the outside world, that's the point. And last but not least, I marked this with little circles. If you do security, one of the, let me say, medium advanced level exercise in security is threat modeling. Threat modeling can be fun. Threat modeling should be taught in, or should be on the education in university. Threat modeling sounds like it's a, let me say, paper exercise. It's not, because the first thing with threat modeling is you identify your assets. What's important for you? What's important for you in your apartment? What's important for you in your apartment which can taken away if you leave the keys somewhere? That's already risk modeling. That's threat modeling. Let's map this to a computer. Which asset would you say is the most important thing on your computer? The answer to this is very wide, but it has a sweet spot. It's typically something even legal people know. It's called the key. The crypto keys. The keys to your crypto wallet, the keys to your conversation, the keys to your network transfer, the keys to your storage. Where are those keys? Those keys are in the little circles. Roll back into your IT knowledge. Those are called registers. Those are little storage memory spots in the CPU. And I can tell you, if your key is not in the register on the CPU, you will be not happy. It will be slow. So that does mean an attacker needs to get access to your register. And that's exactly what we are fearing. This is shared compute, where we as AWS say, well, we are not doing this. At runtime, we are not sharing those cores between two customers, because we have seen things can go wrong. If they go wrong on the CPU stuff, you're doomed. You need to change the physics. There's almost no possibility to patch that. So that does mean if we roll back to the economics, remember the first slide, typically I would say, roll back here, is this possible? No, a little bit. If we roll back lots of slides, if we look into the economics, we need to prevent the attacker to get down there. We need to know that. You don't need to know how the chip is implemented. As a CISO or as a decision maker, as a policy maker, as a manager, you don't need to know how the chip is implemented, but you need to be able to ask the right questions. Am I sharing my resources? If the answer is yes, how do I protect, or how will those resources be protected? And what is the sharing strategy? Those are the important parts. Because we need to make a good risk analytics and make sure the attacker doesn't get down there. And if we look forward now, I can use this slide here. You can do those layers. You can do the right design. You can do defense in depth, like building bubbles, placing somewhere down there in your infrastructure. But you need knowledge to open that. So back to what we have heard. Agents, AI, model context protocol servers. If you want to make real use of that, you need to share your data with your agent. That's the nature, right? I just read a nice article about a newspaper in the Nordics cracking the AI thing for newspapers, because they created AI agents scanning data and pulling together input vectors for the journalists to find stories. They don't use artificial AI to write the story because, well, no one will be able to read this. So I'm a good AI detector, because if you give me a text and I can't read it quick, I know it's an AI thing. And especially in English, as a non-native English speaker, I'm trained on typical book writing, and if it's an AI system, I can pretty nicely say it's not there. So, however, they have a really good public story where they say, well, the magic of AI is coming with combining data sets. And if you combine data sets, you need to share data sets, and that makes your agents the neuralgic point of the asset. If the agent is having your assets in his context, you need to secure that. And this security is going back to confidential compute, because the agent is running on a computer. It's not running in an AI system, it's running on a CPU. You can experience this yourself, open your laptop, start, and I have seen someone outside doing this, having to AI systems, and there's another nice video where two AI systems on the same laptop are fighting each other. So you tell the first agent, well, there's a AI system on the other side, kill it. So computer kill -9. And you tell the other side, well, you know what, there's also another thing, and then kill that. And then you see both AI agents trying to find a way to kill the other process. That's happening on your computer. How does it work? With trust. And that's the other thing which I really want to underline with knowledge. If you have such an AI agent and the AI agent is coming to you and say, well, I have the following thing to work on. I need to execute the following command or the following task or the following job. Am I allowed to do this right now? That's typically an A. Or do you not want me to do that? That's an N. And now I've seen AI agents asking you a third thing, giving you a third option. Do you trust me? The answer is with a T. I have goosebumps just remembering me having this experience the first time. That the AI agent said, well, I want to have access to your file system. Do you allow this once or no, or do you just trust me? Pushing the T button is opening the world to danger. If you play around, if you want to throw away your laptop afterwards, that's fine. If you have a good restore function, go. I just got asked by CISO, well, how do I practice, how do I play, how do I fail fast? Don't on your production system. Because if you trust your agent to do everything, you might be doomed. For those who want to see this in a more funny way, there's a nice episode of Silicon Valley where someone gives his AI agent the task to eliminate all bugs from my code, and then pushes the T button. What has the AI agent done? Delete all code. Yeah, so that's a mathematician joke, that's technically correct. Yeah, absolutely useless. So don't be in this area. Be on the clever area. And now we also come into the point, if we want to fail fast, fail often, without disaster, we need to find the balance point here. So this does mean don't do this with your production system. Do it on a play system. Learn fast there. And know how you share and with whom you share. In the future, we will see more in the confidential compute. Now we see maybe a customer, you. We see the service provider, us. And sooner or later, we see the agent as a third party, which does mean we need to do confidential compute also with the third party. So if I would have a fast forward button, I would do this now, because I'm down to 5 minutes and open to questions. I know it's late.
Nobody? Come on, it's similar challenges like with the Oracle presentation, so probably the questions were exhausted at that time.
Yeah, I really need to organize a wafer and take it with me. But those are expensive things, yeah.
About human aspects.
Human aspects, yeah. The human aspect is first of all in the trust, because all trust in this area sooner or later has a link to a human. So in a perfect trust situation, the trust would come from the highest point, maybe from the CEO or from the company, government or leader. So there's a trust chain, and trust comes in, or the human aspect comes in with designing those access rights. because someone sooner or later needs to give those rights. They're not coming out of nowhere. This is similar like identity and access management topics in the past, where we have policies which need to be written, and from there we need to work on the big challenge, and especially with the physical aspect, is that the human aspect in those chain is before the chip is printed. That does mean we're disconnected. We can't go back. That does mean we need to have possibilities of isolation. That's something I learned in my early ages of IT in the 90s, well, 80s, 90s. If you can't control the human aspect completely, and we need to keep this in mind, and especially here in Europe, maybe we don't want. Maybe we shouldn't. I've been sitting here and heard the GDPR word very often today. Maybe we shouldn't put the human into an area where we limit him. So that does mean we need to create areas where the human can be free, where the human aspect can be free, where the human can evolve. And we need to take this evolution then and carve it into technology. And I think that is something where also AI systems will not take our roles. They will need the root of trust from the human aspect.
Okay, I would have another question. You mentioned that you are already ready. You are already ready for the post-quantum reality.
Yes.
Does it mean that you are already ready to break the existing ciphers, encryption, and so on?
We are more on the defender side.
I know, but
we invested since a decade or longer into being part of the researcher groups which work on the post-quantum area. So we fund several researchers who have been designing those algorithms and which wrote the papers and which did the implementation. So we're more on that side. We are less on the side of finding a way to do prime factor divisions quickly. That's another aspect of the world. Yeah.
Of course, I was expecting this reply, but I was curious, how long do we have until somebody which is not that careful, like a responsible multinational?
Good question. How long do you have time? The time is over since 10 years.
Oh, okay.
Because there's a problem called store now, decrypt later.
Right.
So, and I can tell you...
It was also on screen.
I can tell you, I've been designing storage systems since 20 years, which are capable of reading the complete internet traffic. So, at some specific points, not everywhere, but at some specific points. So that does mean consider your data to be recorded already. As I said, what left your house might be on someone else's disk. So
I was considering stuff like, for example, faking signatures on contracts, on legal documents, or canceling such signatures.
From the cryptographic, let me say, attestation standpoint, that's one of the reasons why the industry bodies and governance standards have pulled up the number of bits in the certificates to an extension where it's unlikely that a post-quantum algorithm will break it. So even RSA, if you just make it long enough, it's not breakable. The main problem here on the technology is if you make the keys larger, you spend more time and space on your network transferring them than the data is, so that you can't do this for everything. You can do this for contracts, but you can't do it for the whole internet traffic. That's just not working. I'm not so worried about contracts. I'm mostly worried that
any legal binding documents which can
legal binding documents or outdated governance certifications. Things where someone created a signature which is valid for the next 10 years and just forgot the bits and bytes. I think that we will find in the industry or in the society, we will find those things later, and then it will be very interesting.
Not to mention cryptocurrency.
Yeah, cryptocurrency is the other part, but you know that some of the blockchains are already poisoned with other stuff. Yeah, so don't download them. It might be illegal in several countries on the world.
Okay, if there aren't any other questions, then I will set for the new break. Any other? No, break? Break it is. Thank you very much, Bertram.